So hello, everyone. Welcome to the CENTRA seminar joined with CAMGSD. So today is my pleasure to introduce Mokdad Mokdad. So he did his PhD in Brest under the supervision of Jean-Philippe Nicolas. And then he did several postdocs, one of them in Dijon, working with José Luis Jaramillo, then in Besançon, working with Thierry Daudet and Nabil Bossot. Then he's now in Grenoble, working with Dietrich Hafner. He was awarded recently with the TIA UK award, and he used this to visit Queen Mary to work with Juan Valiente Cron. His main topics is research in mathematical general relativity. He focuses on scattering, geometry of black holes, decay, and the interior of black holes. And today he will be talking about scattering of test fields in the interior of black holes. So the stage is all yours, Mokdad.
Thank you very much, Edgar. So hello, everyone. Good afternoon, and thank you very much for being here. Thanks a lot for Edgar again for organizing and inviting me to give this talk. I'm very happy to be in Lisbon and finally visiting CENTRA and interact with very nice people here. As Edgar said, I'm going to be talking about some recent development in the mathematical theory of the interior of black holes, namely about scattering of test fields inside the black holes, and in particular in the context of the cosmic censorship conjecture. Okay, so this will be the main topic. And well, before I start, I'm going to assume that everyone is familiar with basic GR. If not, please feel free to absolutely stop me at any point and ask me about anything, any innovation, any question. I will be more than glad to answer. So we're going to start in a spherically symmetric charged black hole. And one of the most typical examples are the solutions to the Einstein-Maxwell system. So it's this system. So G is the metric, and F is the Maxwell tensor, the Faraday tensor. And a solution of this system, which is spherically symmetric, belongs to the family of Weisel-Nordstrom. And if lambda is equal to 0, then it is exactly Weisel-Nordstrom. It's a charged black hole that's not rotating with a mass. And if lambda is positive, then we call this space-time Weisel-Nordstrom de Sitter. If it's negative, then it's anti-de Sitter. Okay, I'm just going to refer to the whole thing as Weisel-Nordstrom de Sitter, anti-de Sitter family. And they are given, the space-time is given by the manifold M, which is R4 minus the origin. And the metric has this expression, and it's characterized by the horizon function F, which has three parameters: the mass of the black hole, the charge of the black hole, and the cosmological constant. And immediately one sees that there's a problem in this expression. Of course, at R equals 0, bad things happen because F blows up. And this is the singularity of the black hole that's part of the geometry. We can't get rid of it. While the other problem is at the zeros of F, right? So this factor blows up. However, these singularities are coordinate singularities, and one can get rid of them by changing coordinates. Nonetheless, there are interesting places, regions in the space-time for these values of R. So R is the radius away from the singularity, the distance from the singularity, and these special zeros of F is the place where are the places where the horizons of the space-time are situated. Okay, so let's take an example where we have actually the maximum number of zeros of this function F, just to make it simple and clear. Let's say it has 3 positive zeros. I'm going to be interested in these 2 horizons. So there will be, this is the singularity at T equals 0. So tau, at R equals 0, tau is the time. This is just a picture of the space-time with angular variables suppressed. And the Cauchy horizon, or the inner horizon, the first horizon near the singularity, is going to be situated at a value of R that I'm going to call R minus. Then it's followed by another horizon, which is the event horizon of the black hole at a value of R equal to R plus. And the interior that I'm going to be interested in is this part, this region, number 2, between these two horizons. Okay, and this picture is the same one, but at a fixed time. So this is just a space-like slice of the space-time. And again, the region is between the two inner horizons. So this is actually a dynamic region in the sense that there is no time-like killing vector field defined here. Okay, and one can see why, for example, for the previous metric, you can see I put the light cones in each region, and in this region it is sideways, which means that the direction going up and down, which is the direction of tau, d by d tau as a vector, is space-like. Okay, while the direction given by d by dr, or the variable r, is time-like. But the killing vector field for this metric is d by dt. It's not d by dr. And therefore, our killing vector is space-like. And roughly speaking, you cannot stay still at a fixed distance from the singularity. You either have to go towards the singularity or outside, depending on your choice of time orientation, whether it's future or past. Okay, so this is a very important point, and you can see that actually between the smallest two zeros, f becomes negative. So f is negative. This is why d by d tau is space-like. Okay, so the takeaway from this picture is that r is going to be my time variable, okay, and tau is going to be my space variable. It's unfortunately confusing in the chair of the black hole, and actually I'm going to make it more confusing to confuse everyone, including myself. So I'm going to change coordinates and define a new coordinate, t, okay, which is defined by this expression, dr by dt is equal to minus f. And if you know this is nothing else but the regular variable, right? But I called it t because it's going to be my time variable. And just to not be annoyed by tau being space, I'm going to rename it to x. And I'm going to change my f from the previous slide to minus f. So what you see here is the minus f of the previous slide. Okay, so why do I do this? Because I'm going to work a lot with square roots of minus f, and I don't want to bother with putting minuses everywhere. It's going to be easier if I suppose f is positive. Okay, beyond this confusion, so you do this change of variable, the metric takes this form, and we see that there is no problems anymore at the value r equal r plus and r minus, but this is just an illusion because all we did is just push them to infinities. And so this is to say that as t goes to plus infinity, r goes to r minus, and as t goes to minus infinity, r goes to r plus. So you can see from this that I'm assuming that the Cauchy horizon is in my future, and the event horizon is in my past. Okay. One last thing, actually, I'm gonna generalize the Rising-Nordstrom anti-de Sitter metric by taking any function f, satisfying these very simple conditions. Okay, so it doesn't have to be of the exact form that we saw before. I just need f to be smooth on a compact interval, and actually this can be relaxed a lot. C2 is enough, but let's keep it for simplicity. And it's defined on any compact interval given by two finite values, positive values, r plus and r minus. I want it to be positive in the interior of this compact and exactly zero only on the boundary at r plus r minus. And I want these zeros to be simple zeros. So f prime at r plus r minus r is not zero. This is the last condition is this part is to ensure that we have a horizon or two horizons. And this part is to ensure that we don't have double horizons or triple horizons because they introduce technical difficulties for the results I'm going to introduce. Nonetheless, they're not fundamental difficulties. It's just like the analysis has to be done completely differently because if you have a double horizon, then everything changes, including the rate of decay of f with respect to the variable t. And this changes everything. Instead of being exponentially decaying, it becomes polynomially decaying, and it needs different tools. Anyway, so this is all I'm going to assume for my general model, and for the rest of the talk, when I want to describe as a strictly symmetric charged black hole, I mean exactly this. Okay, and Well, as I said, we didn't include the horizons because we pushed them at infinity, so we have to put them back in order to do our scattering theory from the horizon to the other horizon. And this is done by the edited Frankenstein coordinates. So you introduce a new coordinates, u is equal to t minus x, v is equal to t plus x. And then the horizon at r minus, I'm going to put it at r minus, it will have two parts, left and right. And similarly, for r plus, the event horizon will have two parts, left and right. And the picture that I would like, you to keep in mind is this one. Okay, so I'm going to try to put it on the board so that with us all the time. So we have our diamond. So this is the interior of the black hole. The space-time itself is given by M. The boundaries are the horizons, with two parts, R plus and R minus. So I'm drawing the Cauchy horizon as being the future, while the event horizon is the past. And just one more thing that belongs to the extended space-time is the cosmic spheres, where two parts of each horizon. Okay, and these are two spheres that one can define new coordinates. You need definite coordinates, the Kruskal-like coordinates, in order to define them. But we're not going to worry about this because we're not going to look at explicit calculations on these. The last thing is that these 2 points, or points of interpretation, are not part of the space-time or its boundary. They are at infinity, and these correspond actually. So I call them I plus because they correspond to the time-like infinity. If you look at the black hole from the exterior. Okay, so however, in the interior they play a role similar to I0, the space-like infinity. Okay, very good. And so if there's no more questions, there is no questions, I will continue and talk about scattering. So I'm going to just give a very broad idea of what's scattering before going to the mathematics. So the idea of scattering is, or the goal of scattering is to summarize a complicated interaction happening with a field propagating in some medium. So let's imagine a classical experiment. You have some object. It could be vacuum. It could be a black hole space-time. It could be a gravitational well or energy barrier or any object that you like. And you have your preferred field, wave, electromagnetic, Dirac, electron, any propagating field. You send it towards this object, and then some part of it will be reflected, another part will be transmitted. And the idea is to try to find or to construct a bijection which associates to the past profile, to the beginning of the propagation, its final form in the asymptotic future. Okay, so scattering, the main object in scattering is the scattering operator or the scattering channel, and in it you want to construct this usually isomorphism between two Hilbert spaces to associate past asymptotic profiles to future asymptotic profiles. Okay, so let's make it more precise. Of course, in mathematical physics, there's different approaches to scattering. Most of the time, they are equivalent. And I'm going to focus on this approach, which is the dynamic approach, also known as the time-like dependent approach, just to represent the results I'm going to talk about later. And this approach is based on what's called the wave operators. So what's the idea here? Well, first we pick our favorite equation. Let's say the wave equation. Okay, it could be anything else. It doesn't have to be linear. It can be any hyperbolic equation where we have evolution. And for this equation, we will define the propagator, which is the solution. It takes initial data phi at time equals 0 and gives you the solution at time equal 2. So ut0 is the propagator of our equation. Okay, and also called the dynamics. And I'm going to refer to it as the full dynamics or the complicated dynamics. Why? Because in this approach of scattering, the idea is to try to find a simplified equation similar to the original full complicated equation, but this simplified one, it's either it's either simpler or you understand better, so that you know its asymptotics in a much more explicit way. And what we want is the following. So we have our initial space of initial data, okay, H, which is usually Hilbert space, and in it we have our initial states, also what's called the scattering states. And for every phi, we would like to find preferably a unique phi tilde, such that if we take phi and propagate it according to the full dynamics, to the complicated dynamics, and propagate phi tilde according to the simplified dynamics, then these two will look the same asymptotically. Okay, when t goes to infinity, these two solutions will have the same profile. And more precisely, what we want is this difference, the norm of this difference, to go to zero. Okay, and it's not hard to see that with some nice properties of these propagators, this limit is equivalent to the existence of these two operators as strong limits. So S here is not a variable; it's just to say strong limit. It's a mathematical notation. And so what would you like here? Like simply a unitary operator or an evolution system, or even bounded, is enough to say that these two are equivalent. And again, it's not hard to convince yourself that if we compose these two operators in this way, then we get an operator which takes me from the past profile to the future profile. Okay. And this is called the wave operator, the direct wave operator, that plus minus, plus for future, minus for the past. And this is the inverse wave operator. So as you can see here, I flipped 0 and t just to say that this is the inverse of the operator t0 w. Okay. So this starts from 0 using the simplified dynamics, goes to t, then from t goes back to 0 using the full dynamics. While the other one does the same in reverse. And if you just think a little bit about this one, you will find that it does indeed describe the bijection that we have. Okay. Yeah. This one? It's just to say that this is the strong limit. So this means that if I put a phi here and a phi here, the limit is this. That's it. So that's not it. It's a pointwise limit. Okay. But usually people like to make it special in Hilbert spaces by saying like this is an operator, not a function. But that's all. It's just a notation of it. But it's literally just a pointwise. Okay, so what's the main motivation for doing scattering in the interior of black holes? Well, it's the cosmological censorship conjecture, in particular the strong version of it. So unfortunately, I wouldn't have time to talk in length about the conjecture itself, but roughly speaking, what it says is that if you have an initial data for the Einstein equation defined on a Cauchy hypersurface, then if you solve for the maximal extension, the maximal Cauchy development, then this space-time will not be will be locally inextendable. Okay, so you cannot extend it locally more in a way such that it stays a regular Lorentzian manifold. So the metric cannot stay regular enough to solve the Einstein equation. Okay, so something has to break down. And of course, in a strict version of this, if I remove generic, then this is not true. Well, almost any exact solution will violate it. Take, for example, the Weisel-Nordstrom solution or Kerr solution, because once you reach the inner horizon, which is the Cauchy horizon, this is what is called the Cauchy horizon, because there's the time-like singularity, and any hypersurface that you take outside here or here will miss some time-like pairs. Therefore, cannot be Cauchy hypersurface. So the space-time intersection as an interior. It's a global hyperbolic, but once you cross this, you lose global hyperbolicity. And then you lose the unicity of the solution. So this is in a nutshell the conjecture. And of course, it's due to Roger Penrose, who was awarded the Nobel Prize in 2020, along with these two scientists. Okay, so that's it. Just a brief history of this scattering business. This started well after he conjectured the cosmic censorship. He did Roger Penrose and Simpson did some numerical work and observed that for electromagnetic radiation approaching the horizon, the inner horizon of a Reisner-Nordstrom black hole, there is a deviation, there is a divergence in the frequency of this radiation. So there is a kind of a blue shift in the radiation, and it blows up. Okay, and this was embedded. And so, what's this idea of blue shift? Instability or blue shift effect. Let's imagine that there is someone emitting radiation or signals from the outside to the interior of the black hole. Okay, they are doing this at fixed intervals of time on a fixed frequency. Okay, so if every second they send a photo for it. But because time is of this like how do you call it? I forgot the word. So because time is compressed, yes. Because time is compressed between quotations with respect to someone inside the black hole, simply because it accumulates here at I plus, then someone crossing the Cauchy horizon would see all of the signals at once, or almost all of them, once you cross the horizon. And as you can see from the picture, even though with respect to the emitter, this is a constant frequency, for an observer here, there's clearly a divergence, a blue shift in the frequency. Okay, and this causes what the hope is to cause a singularity at the Cauchy horizon, and it collapses to space-like singularity, therefore validating the.
One thing that I never understood is that it seems that they have two infinities. One is the blue shift, and the other is the accumulation of light rays.
This one? This one?
Yeah, at the Cauchy horizon, you have the blue shift.
Yes.
And at the same time, the observer is seeing an infinite number of light rays. So there are two infinities.
What's the first one? Sorry, the second one is the accumulation of radiation. The first one is.
And the blue shift.
Oh, this is the blue shift. The blue shift is the accumulation of the.
One ray. You can have an infinite blue shift for one ray, and you have at the same time an infinite number of light rays that we're seeing. So to me, it's two different. Huh? Yes. Two different. Yes.
Yeah, which is gonna make things worse, of course. Yeah, right. So this is similar. This is how I think about it. It's similar to the redshift, the more famous redshift, where you just interchange the roles of the emitter and the observer. Okay, so here the emitter is going inside the black hole, and an observer outside will see everything redshift. Again, probably here is two kinds of redshifts. Okay, so after that, in a couple of years, Chandrasekhar and Cauchy showed analytically that there is actually a blow up in the frequency for the Zarelli-Ricci equations, which are the polar and axial perturbations, gravitational perturbations of black holes. And this was done already also in the Reisner-Nordstrom setting, using stationary scattering. So I didn't talk about stationary scattering, but it's essentially scattering after decomposing on the frequency domain. And so that they proved that there is indeed a blow up for these type of wave equations. And then in the mathematical community for scattering, or mathematical results for scattering, there was a big gap up to 2019 when Christoph Cayley and Jakob Schleppen-Brockmann they constructed a complete scattering theory for linear waves inside dimension. Okay, and there is something very special about the construction in the sense that what they did, construct a scattering operator directly from the horizon to the horizon without passing by an intermediate hypersurface. And I'm gonna explain this more later on. But just keep this in mind, which is not the classical way of doing scattering. Okay, one usually do it on two steps using these wave operators. So you can think of the wave operators as sending data from here to t equals 0 and then from t equals 0 to the other side. But their construction is not based on that. So after that, with Dietrich Schaffner and Jean-Philippe Nicolas, we constructed a scattering theory, also a complete one for charged and massive Dirac fields in the interior of charged strictly symmetric black holes. So I wrote Reisen-Nordström de Sitter anti-de Sitter, but it's actually the general model that I showed you. And after that, so this one I will also talk about it. This one was, we were able to construct it using the classical two steps scattering. After that, I did the equivalent approach using geometric scattering, so what's called conformal approach, also for the Dirac equation of Reisen-Nordström de Sitter, or the same setting of general charged strictly symmetric black holes. And after that, with a friend of mine, Rajan Nasser from ETH, we proved that actually there is a breakdown of intermediate scattering for linear waves inside Reisen-Nordström de Sitter, or any strictly symmetric charged black hole, which explains why these two gentlemen did not do the scattering in two steps. So actually, you cannot do it in two steps. Okay, I'm also going to talk a little bit more about this one. And after that, there were some very interesting mathematical works also on the Cauchy instability. One of them is called Jan Spelsky, and he showed mathematically, he did some mathematical proof for the blue-shaped instability at inside the Kerr Cauchy horizon for spin 2 Tchaikovsky equation, which is linearized gravitational propagation, also based on scattering approach. And also there's a paper by and Stappentoff-Rotman, which is based on the Stappentoff-Rotman-Cayley theory, scattering theory, also to prove Cauchy horizon instability near the Cauchy horizon of a Reisen-Nordström black hole. And the most recent work, up to my knowledge, is my paper with Miro Shkovsky, where we did scattering for charged and massive Dirac fields inside Kerr-Newman anti-de Sitter and de Sitter black hole. So this includes Kerr-Newman anti-de Sitter and Kerr-Newman de Sitter. Okay, so let me now try to talk more in a bit more detail about these results. So the Dirac equation, the way I'm used to do it is in this form. If you worked with Penrose abstract indices, this is exactly the formalism. If not, don't worry, I'm gonna convert this to a simple, or not simple, a PDE system on complex functions.
So why are we doing the Dirac equation and not the simple one?
Okay, so I'm gonna talk about the wave equation and the Dirac equation. And the reason I include both of them is to show that big contrast between these two equations. The behavior is very different. So you would see it's very interesting. So the Dirac equation is given by the Laplacian acting on one spinors, or spin half. So this is the Levy-Schmidt connection, and M is the mass of the Dirac field, Q is the charge, and the Dirac spinor itself, or bispinor, is given by the vector phi chi. Each of them is a spin half spinor. And what makes this equation a charged Dirac equation is the existence of this A, which is a one form describing the potential of the ambient electromagnetic field. So we are in a black hole, which is a charged black hole. This charge is coming from a Maxwell field, okay, which is fixed. We're not gonna couple with it. And then we're not gonna couple our test field with it. So this is fixed. And if you take a potential of this ambient field, this is what's obtained in this equation, and it's the electrostatic potential, if you know. Okay, so why one of the most convenient things about the Dirac equation is the existence of a conserved quantity, regardless of the geometry that you're working on, and this is given by the current of the Dirac current, which is a causal vector field. Defined using the Dirac field itself, simply by multiplying the spinors by their complex conjugates. Okay, and what's nice about this current is that it is conserved in the sense that it is divergence free. Okay, and to obtain this this equality, this identity, all you need is the Dirac equation. That's it. It doesn't matter what kind of all you need is this equation here. It's a simple calculation that follows in 2 lines, and in any background, symmetric, spherically symmetric or not, you will have this, which is kind of a general property for spin half integer. Okay, so and why this is useful? Because one can use it to define a norm on the Dirac fields, and this norm turns out to be actually an L2 norm. All you have to do is project your spinors on bases, okay, spin frames. Think of them as vector spaces, and you have bases, and you can project these spinors into phi 0, phi 1 as components of phi, chi 0, and chi 1 as components of psi. And these are complex numbers now, complex functions defined on the initial hypersurface sigma t, which is. So this is sigma 0, equal 0, and this will be a sigma t. I don't know if you mentioned this, but these are actually Cauchy hypersurfaces. This is why they foliate the space-time, and our space-time is global hyperbolic. So any hyperbolic system is well defined. That's the nice property. Okay.
What is new in this property?
What's new?
So the character new.
Oh, new. This one. Okay. So this is the normal to sigma t. Just contract the current with the normal sigma t. So this is new. And integrate the quantitative. Okay.
So on the right hand side,
This one?
okay. So, yeah.
Yeah, so actually what happens is that you can write this new in a way. So to go from here, you use what's called the Newman-Reynolds formalism. So you define a tetrad, which is a basis for the tangent, complexified tangent space. It has two real vectors, 2 complex vectors. And using this, there is a 1 to 2 correspondence between them and spin frames, basis for spinors. Okay? And these are defined in the following way. So usually we know them by iota and omicron. So for omicron and iota. So this is to say, once you fix your tetrad, you fix up to a sign the basis for the spinors. Okay. And what's interesting is that you can choose these, and this is why the formulation by sigma t is interesting. You can choose this tetrad to be adapted to this geometry in the sense that u is now equal to basically r plus number of squared. Okay. And now if you contract it with the currents, and just know that by definition phi 0, for example, is phi a. Let's carry out the calculations to get exactly this way. Was that your question? And the d volume is the volume form of the surface thickness. Okay. This is a very nice L2 Hilbert space that takes functions defined on sigma t and have values in the Dirac bundle, bispinor bundle. And the norm now is simply this norm, which is an alpine. Okay. Thanks to this divergence-free identity, this norm is conserved between different times. Okay, this is simply a divergence theorem that you apply, and it gives you the unitary evolution of the Dirac field. Okay. After writing the equations in the Newman-Penrose formalism, basically projecting on the tetrad like this one, and doing some simplifications. This one is just to absorb the volume form of sigma t into the field itself, because it simplifies the equation and simplifies the antinorm. You arrive at the Hilbert space, which is literally just L2 of a generic surface, which is R times S2, and takes values in C form. Okay, this is sigma, and it's simply the norm L2 on these functions. Okay, and there's an isometry between our space HT and H. You can write your Dirac equation as a Schrodinger equation with a Hamiltonian H that is, of course, spherically symmetric because we're working in a spherically symmetric space-time, but also more importantly, it depends on time. So this is one of the first differences between the interior and the exterior. The Hamiltonian depends on time. It's a time-dependent Hamiltonian because F itself and R are functions of time. Okay, so this introduces some technical difficulties, but it gives you an easy way to guess what's the simplified Hamiltonian, what the simplified Hamiltonian should be. Well, formally, you can simply just take the limit of this as t goes to infinity. Okay, just formally, just to get a guess. And you see that because as t goes to infinity, r goes to r minus r plus, which are zeros of f, these two terms die out. Okay. And so this term here, d slash is the Dirac sphere on the Dirac operator on the sphere, and sigma 2 and sigma 0 are the Pauli matrices. And so as I said, by taking this formal limit, you get your good guess of the simplified dynamics. You can take another simplified dynamics. It doesn't have to be this one, but this one is very simple and nice to work with. And its functions are constant, so there is no functions anymore. It doesn't come in time. And one interesting thing about charged fields is that the simplified dynamics that you can compare to is usually different on different regions, and this is due to the charge having different values in the future and in the past. And this is, if you take the charge to be 0, you see this term dies out, and you can use the same Hamiltonian on both ends. But because of the charge, one needs to deal with this charge difference. And this does introduce some difficulties, technical difficulties, and you have to do some gauge transformation. You have to use the gauge invariance of your space time, but unfortunately, I wouldn't have time to go into it. Nonetheless, so this is a well-behaved Hamiltonian, and we can define its propagator. And with this setting, we're now ready to state the scattering theory. So we can show that these operators, as strong limits, they exist. The strong limits exist, and they are actually unitary operators on H. And here we can see that this is the propagator of H0, because H0 is time independent. Its propagator is simply exponential IT. While this is not the case for HT, because if the Hamiltonian depends on time, its propagator cannot be in one parameter family of operators. It's a 2-parameter family of strongly continuous operators, something called unitary evolution. And you can prove that these exist, and they are unitary operators, as I said. Moreover, they are inverses of each other, which is a very desirable property. And with this, you can finally construct the scattering operator, and it will be evidently a unitary operator. Yes?
So you're using the H0 plus operator.
Mhm.
Define W plus.
Yes.
And the H0 minus.
Exactly.
But previously, I think you had also plus and minus with the same operator. When you were describing what the spectrum is.
In general, yeah, because I have T plus and T minus as limits.
Right.
So this is what I have.
But this is slightly different from what.
It's the same.
that we have to operate.
It's the same, but the two operators, yes, are different because we take different limits and also because of the difference in different asymptotics. And this is a very good question because actually what you need to do to glue these together, you need to do a gauge transformation that takes care of this change in charge. So you have to multiply somewhere here. Well, this is not something, but if you want to take into account the geometric interpretation of these operators, then one has to introduce an operator that changes the gauge from this limit to the other one. Okay, and we can start this level. Okay, so any other questions? Okay, just a quick look at care. Of course, we're not gonna do any calculation there, but this is the care, and the people who work with it, it's infamous for its complicated expressions. I just want to point out that so this is the care metric, and this what plays the role of our horizon function. Right? So this is what plays the role of the small f of r. Okay, and one can do the same for the drag equation. Much more involved in calculation, but nonetheless doable. You can cast it as a Schrodinger equation with this Hamiltonian, which again depends on time. I don't know why I have tau, but sorry for that. So tau is time. Okay, so as you can see, it depends on time. And again, you can take a good guess about the asymptotics by just simply taking limits. And this F theta, which I forgot to define, is simply just a square root, more or less. It's just simply a square root minus square root of this. Okay, so it does go to zero. It does go to zero at the horizon. So what would be left for the asymptotic behavior, the asymptotic Hamiltonian is this part, which is which when you take the limit, there will be a constant here, just r plus or minus. And the main difficulty in care in comparing to the Reisner-Nordstrom or the systematic case is this operator, because in the other case, well, essentially how do you prove the scattering, how do you prove existence there? You do a decomposition of the spherical harmonics. So you land on a 1 plus 1 equation, and then you use basically Cook's method to prove the existence of the strong limits. However, here a decomposition is very, very hard to obtain 1 plus 1. Maybe it's doable, but it's not convenient for scattering, and especially because of the time dependence. There are some decomposition, but it usually depends on the frequency. And in this case, it would be very, very, very difficult to deal with because the Hamiltonian depends on that. So the main difficulty comes from here because you can't diagonalize this operator anymore. And moreover, it does not commute with the Hamiltonian. And so probably half of the paper is just dealing with this operator. But nonetheless, you can bound its action on the propagator uniformly by the norm of the initial data, a Sobolev norm of the initial data. Okay? And once you have that, the other terms are relatively easy to deal with. And you obtain also a scattering theory using the wave operators. Again, this is almost exactly the same theory stated, but just for the different cases. Okay. And with this, I'm going to move on to the wave equation, if I still have time. But,
5 minutes.
5 minutes?
Yeah.
Okay, so I have to,
A bit more than.
a bit more? Okay. Maybe 10 minutes?
Something in between.
So the geometric wave equation is this, the Eigenvalue. Phi is a scalar field. Probably you know this one. It's not important, but what I exactly use. Right here. And an important object for the wave equation is the energy momentum tensor, which is basically defined using the derivatives of the scalar field. It also has, similar to the Dirac current, has nice properties of being divergence free. If you have a solution, then the divergence of TAB will be 0. And it also satisfies the dominant energy condition in the sense that if you contract it with a future-oriented causal vector, two causal vector fields, x and y, you get a positive quantity. Okay, and why this is important? Because one can use it to define energy. So you pick your favorite vector field, which represents your reference frame or your observer, and as a hypersurface S. One can then contract with x to obtain a current which is integrated along S to obtain the energy of phi with respect to x across S. Okay, and why this is an energy, why this is interesting, because if x is time-like and S is space-like, then this would be a definite positive quantity. Okay, i.e., it defines a norm on the solutions of the wave equation. Moreover, if x is given, then this quantity is conserved. Okay, by the divergence theorem. However, the main difficulty, and it's a big one, inside the black holes for the wave equation, there is no conserved energy norm because, as I said before, there is no time-like Killing vector. So you have to choose between these two nice properties. Either you take a Killing vector field, but then you don't have a norm, or you choose a time-like vector field, but then it's not conserved. For scattering, it's much more preferable to have a norm because you want to have that space. So nonetheless, you do. Okay, so you take a vector field. In this case, you're going to take it to be d by dt, and the surface S is going to be sigma. Okay, and you do the calculation, and if you work with the wave equation, this should be familiar to you somehow. It's the energy of the wave equation, which is basically an L2 Sokolov norm of other two. Sorry, L2 on the derivative of the solution. Okay, one can do the same. So this is for sigma t. One can do the same on the horizon. Okay, now I take S to be the horizons, each part of them. T itself extends smoothly, although small t as a variable becomes infinity, but the vector field is well behaved. And one of them, a homogeneous Sokolov norm, okay, so that contains only derivatives of the vector field along with respect to the variables, the nature of variables on each horizon. And with that, defining the energy, the finite energy spaces, the Hilbert spaces, is simply just taking completion of smooth, compactly supported data with respect to these energy groups. Okay? Yes? For this one? On the horizons, no. We don't need on the others. Yes, it is a norm as a norm in the sense of an H.1, a Hilbert homogeneous Sokolov space. It's not a distribution space.
Right.
Yes. Yes, we do. But if you start with smooth, compactly supported data, then your function will be zero somewhere. And for completion of this data, this is. But you're absolutely right. Take any function, it can be known. Okay. But this is a particular Sokolov space. Especially in dimensional. Okay. So what are the results in these settings? So we have the theory by Cayley and Shabbat-Rothman, which says that in the case of Rajah-Nordstrom, and now we have to precise that lambda is equal to 0, you will see that the wave equation is very sensitive and delicate. They define the scattering operator in a very simple way, not using the wave operators, but they define an isomorphism between the energy space at the event horizon in the past into the energy space on the Cauchy horizon by the following way. So you take data on your event horizon, and then you solve the characteristic Cauchy problem for the wave equation. You extend the solution up to the event horizon, and the image by the sketching back of this data will be the extension of the solution on the Cauchy horizon. Okay, and the solution is phi, and phi minus is the initial. Okay, but they also prove in their paper, in their work, that there is a breakdown of scattering if you turn on lambda. I guess they only consider lambda positive, if I'm not mistaken. So if lambda is positive, then the picture is very different. You do not have scattering anymore. The scattering operator will not be an isomorphism. It will actually be an unbounded operator. Okay, why? Because you can find data smooth, compactly supported on the event horizon, normalized, a sequence of data, normalized. The energy is equal 1 to all for all n, but the limit of this sequence, or the limit of the energy on the solution on the event on the Cauchy horizon is equal to infinity. Okay, which means that the operator cannot be bound. And the same happens if you add mass. Even if lambda is equal to 0, if you consider the Klein-Gordon equation, which you just add a constant times the vector field, times the scalar field, then also you will have this breakdown. Okay, and this is true for almost all values of lambda, in the precise sense that for almost, there's only a negligible set where this does not happen. Okay, and finally, if I still have a little bit, so this is the result of the breakdown of intermediate scattering. So as I showed you here, this is done directly from the horizon to the horizon. However, the classical way of constructing scattering is to do scattering from the horizon on past infinity to a finite time, then from there to the future. And what we did is we consider these operators that are defined in a very similar way. You take data here, you look at the solution here. Okay, or rather, you take data on the Cauchy hypersurface, and then you solve that non-characteristic Cauchy problem now, and to obtain the traces of the solution on the horizon. And these operators are called the trace operators, okay, which are denoted by P plus minus. H0 is the finite energy at sigma 0, and H plus minus are exactly the same as before. And that's what I just described, the trace operators. And these operators extend to be linear bounded operators. However, they do not have bounded indices. Okay, and the reason is the existence of a sequence of data on sigma 0, which is normalized against, not completely supported. However, the energy of this sequence on the horizon as you approach the horizons goes to 0, which means these operators cannot be cannot have bounded indices. Okay, it's very interesting. The reason is very specific, so we managed to pinpoint exactly what's the reason of the failure, and it's due to the behavior of the solution at the frequency equal 0. Okay, the spatial frequency in some sense. So you take Fourier transformation with respect to the spatial variable, and it's literally just this. If you remove this 0, there's also a condition in the angular mode. If you remove this, then you get scattering, intermediate scattering. And this is interesting because the frequency omega 0 is also responsible for blue shift instabilities. And this can be seen in the paper of Luke, O, and Stapel. Okay, so one last slide.
Yes, one.
So just to go back to the cosmic censorship conjecture, or at least to touch on it, there is also some C1, what's called C1 blow-up results. And these are results of instability in the sense that the solution of the wave equation in the Rhizon-Washron case, okay, again, lambda is equal to 0, you have a breakdown of the regularity of the solution at the Cauchy horizon. So what's happening here? There exists some smooth, compactly supported data, which is supported here, and actually you can take it to be supported on one part, such that the solution on this part of the horizon is not differentiable in the direction transverse to the horizon. Okay, so because d by dt is killing, regularity in these directions is transferred. So if the solution is regular in these directions, its image is regular in these directions, in the tangential directions. But if you take transverse directions, then it's not the case anymore. So the solution to the wave equation is not C1 here, and actually it's not C1 anywhere on the Cauchy horizon, including the crossing sphere. Okay? The way they do it actually, or the way you do it in general, is you show that there is a blow up of the derivative on the crossing sphere, and then you propagate the singularity along the horizon. Okay, and very important thing, at least for me, it was very interesting to see explicitly these conditions appearing in the calculation. So you explicitly see that the blow up happens exactly because kappa minus is less than minus kappa plus. I remind you, kappa plus, kappa minus are the surface gravities of the Cauchy and the Cauchy on the other horizon. So I find simply to be the value of f prime at r plus r minus. These are called the surface gravities of the horizons. And if you have this condition, which is automatic if you have Reisen-Nordstrom with two solutions, with two zeros, two horizons, then this condition is automatically satisfied. Now there is an almost finished work. Well, let's say, so we believe we have the result, but let's say for the sake of being scientifically, I don't know how to say it. So just let's say that this is true. Hopefully this will appear soon on my type. We showed a similar result for the Dirac fields, C1 dot result for the Dirac field in the general spherically symmetric case. Okay, so now f with any function, it doesn't have to be Reisen-Nordstrom. And it's a similar story. So you have data here, which gives rise to the solution, which is not C1 in the direction transverse to the horizon. But what's also very nice, and this is kind of not trivial to find, because one has to choose very specific spin frames that gives you right weights to obtain the C1 blow up. And what's I find very interesting and very nice is that this condition is required. So a priori, you don't have any condition on f prime, on the values of f prime. But in order to obtain the C1 blow up, you need to impose this condition. So I was very happy to see this when we did the calculation. And if I remember correctly, probably years ago, I read somewhere in the physics literature that this condition is well known to be a necessary condition for the instability of the Cauchy horizon. But to my knowledge, these are the first times when I see them exactly appearing precisely in the calculation of a mathematical study. And yeah, with this, I would like to thank you very much for listening. And so
Thank you, Mokdad. That was perfectly on time. So we have time for one or two very quick questions. Yep.
What is the difference between the stability and the reactive?
Oh yeah, yes. I should have said that, but so the main difference is that the Dirac field, the scattering for Dirac field, where there is two main contrasts. The first one is that you can construct scattering theory for Dirac fields using intermediate scattering. So you can go from the horizon to a finite outer surface, but you cannot do it for the wave equation. Okay, so this is up still to now. I don't know what's the physical interpretation for this breakdown of scattering for the wave equation. I know precisely mathematically it's due to what, but I have no idea about what kind of physical mechanism to do this. I think people think that it is related to blue shift, but I don't think anymore. Anyway, so this is the first difference. The second difference is that Dirac is much more robust in the sense that it does not break down if you change the parameters of the black hole. scattering itself. So even from the horizon to the horizon, you will always have scattering for Dirac for any charged strictly symmetric black hole. While for the wave equation, it's much more delicate. Almost immediately you lose scattering if you turn on the cosmological constant or if you don't on the mass. And these two differences are very interesting to see because they do not happen in the exterior. So in the exterior, the wave and Dirac behave almost the same. They have a very, very similar structure for the scattering, but in the interior, it's a completely different story. And it's nice to see these two contrasts between these. Thank you very much for the question.
Any other final question about that? If not, let's thank the speaker again.
If you enjoyed the video, like and subscribe.